Okay, welcome back to the math zone. So we're going to start solving differential equations. We've dealt with equilibrium solutions, which are the simplest type. Now we're going to look at the next level above that, which is a separable differential equation. Let's have an example. Okay, so here's our separable differential equation. What we can do, and it's maybe not 100% kosher, but we can treat this derivative as if it was a fraction. I'll do it both ways. Okay, so first I'll do it the simple way. The simple way is we multiply both sides by dt. Okay, and then we can integrate. So we have the integral on both sides. Okay. On the left-hand side, this is really the integration of 1 times dy. The integration of 1 with respect to y is y. On the right-hand side, we have the integral of cos, and the integral of cos is sine plus a constant. And if we're not sure, we can always think, well, the derivative of sine is cos, so yes, we have integrated correctly. Now we need a bit of extra information, so this is called an initial condition. This is saying when t equals pi, the y value there is 2. So what this is essentially saying, right? dy dt is cos t. So it's something like this, I guess. I don't know. And then we take a single point somewhere, and then we trace through the slope field. Do you know what I mean? So this equation is describing the rate of change, and then the way we get a curve is we have our rate of change plus we start somewhere, and mathematically that describes a curve, if you want to think about it philosophically. So we put that information in down here. So we say when t equals pi, y equals 2. So we plug that in. Y now becomes 2. Sine of t, but t is equal to pi. And sine of pi is 0, so we have 2 equals c. That's our solution. So then we can put that back in and say y equals sine t plus 2. There we have it. So like I said, this is kind of the slightly cheating way, and some people don't like this way. So here's the more rigorous way. The more rigorous way is we take this equation and we integrate both sides against t. That means we take, and then we say, well, on the left-hand side, this integral is really, we can make a change of variable, something really silly like let y equal y or something. And we basically do u substitution in the integral just to switch this out. So then we do a bit of u substitution. It's nothing too exciting, and it does come down in the end to a transformation of variables, which gives us the same thing as if we had treated it like fractions. So I often say this, calculus was the internet of the 1700s, in the sense that it came along and people could suddenly do a lot of very cool things, and no one was really sure how much of it was legal. And then it was studied more rigorously, and some of it turned out to be okay, like the treating like fractions, and some of it was not so okay. But hey, you know the only way to improve is to do 1,000 more problems. So let's go ahead and do that. Okay, fair enough. So just like before, first step is isolate everything. These are called separable differential equations because if we treat everything like division and multiplication, we can always get things on the right side. So I want all the y stuff on the left side, all the t stuff on the right side. Okay, I've got that set up. I can now integrate. Okay, so the integral of 1 on y is log y. Really important to remember to include the absolute value signs. The reason is that log of a negative input is not defined. However, the integral of 1 on y is defined for negative numbers. So to protect ourselves, we include the absolute value signs. This is a common mistake that I see people making, and just be careful about it, okay? So now we can exponentiate both sides, and we get that. However, c is a constant of integration, so we can apply the rule, and really we have this, right? Absolute values there. So we split that up, and then it's very common to do all of this in one single stroke. So we get rid of the absolute values, and then instead of e to the c, we just say it's some unknown real number. There we have it. And now we apply our initial conditions. So y equals 2 when t equals pi. Let's put that in. Y becomes 2. Then we have a sine of pi. Remember, sine of pi is 0. So we have times e to the 0. And anything to the 0 is 1. So this is really a equals 2. The first step is we need to factorize this so that we can isolate things. So we have a common factor of z on the right-hand side. We'll pull that out. We can now do the normal task of isolating. Okay, I'm going to kind of speed things up a little bit. So really, I'm integrating. I'm not going to draw integration signs, but that's what I'm doing. So the integral of 1 on z is log z. Don't forget the absolute value signs. The integral of the right-hand side, well, integral of 1 is t. Integral of t squared is t cubed over 3. Don't forget our constant of integration. So why not? I will go ahead and exponentiate both sides. Just using exactly the same pattern as I did in the question before. So we've got z equals a real number times e to the t plus t cubed over 3. Just exponentiating there. Okay. Now we can apply our rule. When t equals 0, z equals 5. So for z, we swap out 5. Then we have a times e. Well, if t is 0, then all of this power is 0 as well. And e to the 0 is 1. So we have 1 times a. This gives us our solution. Z equals 5 exponential t plus t cubed on 3. Awesome. There we are. Okay, well, this seems okay. Let's go ahead and first step, isolate. Okay, second step, integrate. So on the left-hand side, I have 1 over y squared plus 1. I just burn this into my memory. I remember that the integral of this is arctan y. On the right-hand side, this is really 1 times dt. So that is t, and don't forget our constant of integration. Now, I could solve it like this, but I'm just going to apply tan to both sides. So if arctan y equals this, then y itself is tan of t plus c. Got it? Okay, now I apply my conditions. So y equals 0 when t equals 1. And we could look at this and we could say, okay, well, c has to be -1 because that would give us tan of 0, and tan of 0 is 0. However, that's not the only solution because tan is a periodic function. So there's a number of points where tan is 0. It's just any multiple of pi. So we say 1 plus c equals n pi, where n is just any integer. And rearrange that, and we get c equals n pi minus 1. And so our final solution, y equals tan of t plus n pi minus 1. Very exciting. Actually is very exciting because we've got a family, an infinite family of solutions there. Remember, an equation is either not solvable, or it's solvable with a unique solution, or it's solvable with a family of infinite solutions. Same thing with differential equations. Okay, this is probably a little closer to the types of differential equations you'll be seeing because it needs a bit of rearranging. First step is I'll get the, I'll just isolate things. So I'll say x y dash equals y squared minus y. Okay, in which case y dash equals to y squared minus y, but I'm going to factorize that as y times y minus 1 over x. Okay, and don't forget y dash is dy dx, so we can swap that out as well. Make it look a little more familiar. Okay, now we just isolate both sides. And we could integrate, however, this term here is not so great for integration. What we can do instead is we can do partial fraction decomposition. Remember, partial fractions are not an integration technique, they're just an algebra trick. So what we've got is we've got 1 over y times y take 1 equals something over y plus something else over y take 1, because we've got linear factors, so the denominators have to be of order 1 less than that, constant. Okay, now we can multiply both sides by y, I'll write this in, multiply both sides by y times y minus 1. Okay, in this case everything divides out and we get 1. In this case some of it divides out. So what we could do is we could expand and solve it that way, but I like to strategically plug in different values for y. So I'll say let y be 0, then I get 1 equals, well, 0 minus 1 is -1, so we have -1 times a, plus now we have 0 times b. So in other words, this tells us our a coefficient is -1. Then I'll say let y equal 1, because that will get rid of this bracket here. So I'll have 1 equals a times 0 plus b times 1. Okay, now I can integrate because I've got it down, decomposed into nice terms. I know it doesn't look nice from looking there, but it's good. All right, so over here we have -1 over y plus 1 over y take 1. Right, so the integral of 1 on y is log, but don't forget we have negative log. And it's the same thing with y minus 1, just by simple use substitution we get the same thing. And here we have log of x. Don't forget the constant. Okay, awesome. So We could exponentiate both sides, but first of all, I'm going to combine on the left-hand side. So I have log of, this is log of y minus 1 minus log of y. So difference of logs is a division. So we have y minus 1 over y equals, and then on the right-hand side, just the standard log x plus c. Okay, now I exponentiate both sides. I exponentiate both sides. On the left, I have y minus 1 over y. On the right, I have, well, really I have a times x, right? Because this is, you know, e to the c. Yeah, okay. Then I use the fact when x equals 1, y equals negative 1. So put that in here. When x equals 1, so we have negative 1 minus 1 on the top, negative 1 on the bottom. That equals negative 2 over negative 1, which is positive 2. And then over here I have a times x, so a times 1. So there I've got it. And my solution is y minus 1 over y equals 2x. I could rearrange that. It's fine. It works just fine. Wow. So a little whirlwind tour of separable differential equations. In the next video, we're going to be looking at general first-order differential equations using something called an integrating factor. This one's going to be a little more theoretical, but you'll see, it's fun. Trust me, it's fun.